All right, so we are now beginning number 19, which is interpreting regressions. And so let's dive in with something that you probably remember. Maybe you remember. I hope you do. There are basically two kinds of predictions you can make with regressions. One is if you have all the various values for a country variable, you can predict a certain outcome. And two is if you change any one of those variables, you can predict how much the dependent variable will change. So this is our regression from, I think it was a week ago, I believe. It was 2 classes ago. This is our housing price regression. 79 plus 237 square feet minus 23,792 miles. And there's an epsilon in there. We're not going to get into that. I sort of tilted that up. That's fine. That's artistic. Keep in mind, too, that when I write variables, I like to write them in caps just to emphasize that they are the variables so there's no confusion. Ideally, I write them as single letters, but I wanted to be really clear as to what we're talking about. So just as before, this is square feet, how big the house is. This is miles, how far away the city is from the center, in miles. And of course, the price is how much the price sold for. How much the house sold for. So, let's imagine that we had a house that was 2,000 square feet. And it was 3 miles from the center of the city. What do you expect the price to be? What would you expect the price to be? What would be the predicted value? How would we figure that out?
The numbers.
Mm-hmm. And when we plug in, you mean put the 2,000 here? Exactly. And you would get something like 79 plus 474 000 minus 71 376, and that of course would equal $402,000 and with $402,703. About $400,000 house is what we would predict. So let's imagine that we see a house that has a price of, say, $300,000 or $200,000, way below what we would expect. What would we think? I like that. What do you say? Say that again. How much work does that house need?
There's another variable that's influencing the price.
Mm-hmm. Right, which is what Rebecca was saying. Like she was arguing that it was. I got that name right. Yeah, great. What Rebecca was saying is that there's a quality of house variable that we don't have in our regression. So maybe that house is in terrible condition. Right? And if we would include it, we'd be able to. I don't know how to measure quality like that. That's a hard thing to measure numerically. But that would throw it off. Could it mean anything else? What other reasons would a house be worth less if it wasn't for size and distance from the city?
I think it's old.
If it's old?
Really old.
So even if it is in good shape, maybe there's a risk that comes with it, right? There's a friend of mine who bought a really old house, and I think they used aluminum wiring or something. No, not a really, really old house, but a house that was built at a time when copper prices were really high, so they used aluminum to wire the house, and it was a huge, they had to get the whole house rewired. It was a disaster. It was a fire hazard. And then she was like, if you buy a house, I think it was I want to say it was in the 60s or 70s. I can't remember when, so be aware of that. Have you heard something over here?
Yeah.
That's true, but usually the house has been on a long time because of some other reason. Right. That's why no one's grabbed it. Yeah.
They're trying to sell us.
Oh, so maybe people are desperate. They want a quick turnaround. But that's interesting. Yeah. So you don't know the motivations of the seller.
Should just be in a bad neighborhood.
Could be in a bad neighborhood. That's what I was thinking. Right. How do you define bad neighborhood?
Maybe there's a lot of crime in the neighborhood.
Mm-hmm. Another thing too that matters a lot is the schools.
Not a good school.
Yeah. So for those of you who aren't from the U.S. and don't know how the U.S. school system works, it's really dumb. And public schools, so like the property that people get, property taxes people pay, go to their local school district. It's not pooled, and then it's like doled out from a common pool. That means that nicer houses typically have more money for their schools, typically have better schools. It's really stupid. And then like where you live is tied to where you send your kid to school. So one of the things, if you ever look for houses, one of the things they'll have is they'll have the ratings for the schools in with the house. This is how good the middle school is. This is how good the elementary school is. This is how good the high school is. Maybe this house has shitty schools. So there's lots of other things. There's lots of other variables that maybe we didn't or couldn't include, but it tells us something about what to look for, right? The price conveys information. Similarly, too, if the house is going for $600,000, that also tells us something. Maybe it's really amazing schools. Maybe it's located right next to a metro stop, right? You can be 3 miles away from the city center and be in a not walkable neighborhood. You can be 3 miles away and be in like a really great neighborhood, one that has really great public transportation access. Right? You can have really great schools. It can be in amazing condition. It can be really quiet, whatever it is. So maybe prestigious too. That's another thing. Like, people love that certain neighborhood names. Maybe it's in a really hip neighborhood. And it tells us something. Now, different story. This was our predicted value. Let's go something slightly different. Let's imagine David has a house and he wants to add a 200 square foot room to the house. So my square feet increases by 200. What should I expect the price to change? How would I expect the price to change as a result of that 200 square foot room? Exactly. Increase by 47,400. Price. How did you get that, Adam?
Because you're just increasing the square feet. Variable at 200, so it's just one zero. So 40, you just said about before it was 474,000. So one zero is 47.
Is anyone confused about what's going on? No, everyone gets it. So often when I do this for exams and so forth, and I ask people, what happens if price increases by this? People want to also reference this, the intercept, or they say, well, I need to incorporate the miles. Do you need to do that? Why are you shaking your head, Ike?
You don't need to do that?
Why?
Because it's the math from the square feet.
Why can I do that?
Because you want to know what the price is of a certain at 2,000 square feet.
Yeah.
So you can just adjust it.
But even if I don't know, like even if I say, you know what, you don't know the size of my house, you don't know where it's located, but I want to know if I add a 200 square foot house, a 200 square foot room, how much would the house price change?
Because you only need the coefficient for the square feet.
Exactly. Did everyone follow that? You only need that 200 square feet. Does anyone know why mathematically if that's the case? The math behind it?
You're only increasing one variable.
So
Everything else stays the same.
Everything else stays the same. So I'm going to abbreviate price P And we would say change in price is the same thing as price now minus price before, right? Which would be, that's the same thing as, this is the price now, 79 minus 237 square feet. I'm just going to call it S. Square feet now. I'm sorry, plus. Minus 23,792 M now. So this is the now price. Minus the before price. 237 square feet before. 23792 miles before. That equals the change in price. Does everyone follow me? So mathematically, what can I do, CJ?
You could put the square feet in SP and the miles in.
Well, let me ask you this. Algebraically, what's something I can do here?
You can plug instead of SB, you can put SN plus 200, and then you'll cancel everything out and distribute the negative. Everything cancel out both sides with 230.
That's what I want to do. Let's start with distributing the negative. So now I have this, right? Does everyone agree I can do that? And then as Adam points out, this cancels with this. That M now is the same thing as NB because I didn't change the location of the house. I'm saying all things being equal, I just added 200 square foot room. So that means that this value is the same as this value since this was negative, this one's positive, so this also cancels. And I'm left with change in price equals 237 S now minus 237 S before, which equals 237 S now minus S before. In other words, change in price is 237 change in square feet. I add 200 feet, 200 square foot, and then I just take that 200 minus times 237. That's my change in price. 47,400 or 47,400. Any questions? In case you doubted me that you could do this. And this is what's so fun. This is what's so powerful about multivariate regressions. Holding everything else the same, like location, you can isolate effects of any particular thing. And therefore you can see not only if certain things are important or not, but how important they are. Yeah?
Don't they cancel out with the things the concept of things that
The SN and SB? But they don't because S now is different than SB. The miles were the same because I didn't move the house. But the square footage now is bigger than the square footage before. So these are not the same variable. As Adam pointed out, I could note that S now equals SB plus 200 because it's the same as what it was before plus 200. And if you want, I can take that. That means that would be SB plus 200 minus the SB it was before, which is obviously just 200. It's the same thing as a square change in square feet. Did you follow that? I felt like I went through it pretty quickly. 200 is, I'm assuming I'm adding a 200 square, I'm adding a room is 200 feet.
Question. What's the triangle?
Triangle means change. Because who has time to write PN minus PB over and over again? I got things to do. Change. Oh, 474,000 is 2,000 minus times 237. Just 71,376 is 3 times 23,000 is 792. Assuming I did that math right, but I think I did. You get looked out, Cole?
I thought you said like you added 200.
Oh.
So I
Oh, I'm sorry. These are two different things.
Oh.
This is if I have this information about the house, what can I expect the price to be? This is if I change something about the house, how can I expect the price to change? So I'm just changing one thing over here. Here I'm estimating something. That's why I say there's two different things you can do with these regression lines. Any other questions?
So we got 237. What do I see with that?
Well, one thing you could ask yourself, let's see, wait, how much? Oh, 47,400. One thing you can ask yourself is the value of the house will increase by 47,400. If someone tells you it's going to cost you $60,000 to build the house, to build a room, you might be like, maybe that's not worth it because the house is only going to get, $47,000 more valuable, and I'm paying $60,000 to get that. That seems like a great deal. It still could be, right? Because this is how much the market would value it. You might value it a lot more. But if you're trying to flip a house or something, you're trying to figure out how much bigger we should make this house, then that's what you care about. It doesn't pass the cost-benefit analysis. Yeah?
So how much is the house is like 100 miles away?
I'm glad you brought that up. What would be the value of a house if it had a square feet of, I don't know, it's a 100 square foot house. And, well, let's not use 100 because you just use 100. Let's say it's a 300 square foot house. And it's 100 miles away. What would you think would happen if I did that? It would be negative, right? It would clearly be negative because you're thinking 100 times. So it's already like that. That's like, what is that? That's over 2 million, right? So I'm glad you brought that up, CJ. This highlights the limits of these regression analyses. And this occurs too because you can do a regression analysis by making a year a variable, and you can project things into the future. But you are prisoners of the data that you're working with. We do not have any house that's 100 miles away from city center. We also don't have any house that's anywhere near 300 square feet. Does anyone know how big 300 square feet is?
Very small.
Yeah, it would probably be smaller than this room. I would assume so, yeah, right? Because 100 square feet is a 10 by 10 foot room, right? Which is a very small room. It's like a... Yeah. Yeah, maybe a master bedroom, so 3 of them, and that's your whole house. That's a pretty small house. There's a show called Tiny House Hunters, right? So if you ever want to get an idea on what a 300 square foot house looks like, go work on that show. There's one room. We'll put the bed up there. So you have to climb into the bed, and then your bathroom it's really just like it folds out. It's like weird. These are very small houses, so we don't have any tiny houses. We certainly don't have any that are that far away. When you project outside the bounds of your original observations that the regression is built off, you are just setting yourself up to look stupid. It's one thing, for example, too, if you want to say you have data on the past 20 years of, I don't know, sales for your company, and you want to say, well, what can I expect sales to be next year? That makes sense, right? That's pretty reasonable. You project what the sales is going to be in the next 40 years, now you just look stupid. You have no idea what's going to be like 40 years. Just like I don't know what things are going to look like if I go way beyond the bounds of the original data. Because quite frankly, going 100 miles away from the city center is probably going to mean I'm in the middle of a different city. Right? Doesn't make any sense. So my lesson for this is don't take things too far, right? Be very careful about being too worshipful of these regression lines. They are prisoners of the data themselves. So really look at your raw data. This is especially true. I see this a lot happening. People usually don't happen with the panel data, but they do it a lot with time series. So like, oh, I know what's going to happen in the future. You see this with like the census, and they say, well, this is what you can see. Census kind of reflects, like, so when some people like are projecting population, you can kind of see that when they're like trying to figure out, okay, how much is Social Security going to cost us in like 30 years, and they will have some like, regression line, which is going to be a trend line, and then they will switch to the dotted line, which is the projection, and then sometimes they will have like these lines right here. These are confidence lines, and they note that as things get farther and farther in the future, I know less and less about what's going on. Right? It could go, yeah, my best guess is right here, but I'm recognizing that it's more wild, right? I'm not really sure. Right? It could also be down here because the regression gets less and less reliable the farther you project into the future, or the farther you project beyond the bounds of the original data. Right. Any questions? Great question. Sorry, I stole this. Okay, I have another question for you. Speaking of data, does anyone know what the current unemployment rate is as of, I guess it was March 2018, right? That's the latest one, March 2018. Great, you can tell me what it is. 4.1, so let's round that down to 4. It's a great employment number. We have a 4% unemployment rate right now, which is really low. Let's imagine that next month, I should say, it's really bad, and it goes to 7%. How would you describe that increase? Aiden, how would you describe that increase from 4% to 7%?
3%.
A 3% increase. Does everyone agree?
Yeah, it's 75%.
It's a 75% increase. Wait. How did you get 75%?
Because 3% is 75%.
Mm-hmm. So going from 4%, so a 3% increase from going to 4% to what would be a 3% increase?
3%.
Exactly. This is a 3% increase. Because as you point out, you take 3% of 4, which would be 0.12%, and then you add it on. That is a 3% increase. This is a 75% increase. Because you take 75% of 4, you get 3. 3 plus 4 is 7. Oh, that's annoying, though, to have to do. I mean, that was an easy one, but, like, how do you do it if it goes, like, 5.5 to 8.6? Oh, that's annoying. Is there another way we can say that? This is what we call a 3 percentage point increase. Don't get those confused. You look stupid if you do. 3 percentage point increase. Or you consider, it is essentially as you would think. A percentage point would be just a 1 percentage point. Let's say. So going from 5% to 6% is a 1 percentage point increase. Going from 12% to 14% is a 2 percentage point increase. That's how you translate it to linear. This is critical because people will sometimes get this confused, or people don't think about it always. Like, let's imagine that there is a 1% chance of having a heart attack. And they say, oh, you know what? If you, and this is all hypothetical numbers, if you eat red meat, It will increase your risk of heart attack by 20%. Does that mean that it's a 21% chance of a heart attack? No. What does it mean? Exactly. That's not nearly as scary. 20% sounds terrifying, right? But it's a 0.2 percentage point increase. That's not nearly as terrifying. So when they say a 20% increase, I don't think they're adding on the numbers. It's a multiplicative, not additive. And that's going to be crucial when we interpret regressions. What was that? There it is. Ooh. Here's sales data for a particular company. Again, a hypothetical regression just to make clean numbers. And I don't want to try to find data. Of course, in thousands. And we are considering the number of rivals a particular store has. I think this is like a home improvement store, and so that's why it also matters the percent of people who are homeowners. I think that's what I was thinking of when I wrote this. Oh, percent homeowners. Again, pretend it's straight. So this regression predicts weekly sales in thousands of a home improvement store location based on the number of rivals and a 20-mile radius and the percent of people in that radius who own their home. What? How would I interpret this right here, this percent homeowners? What does that 300 mean?
I want to call him George. George, what does that 300 mean?
People that what?
Those that own.
Those, well, that's what the variable means. The variable is the percent of people in a 20-mile radius who owns the house. But I'm multiplying that number by 300. Why? What does that 300 mean?
Like the sales go up 301 every time the whole ownership increases 1%.
1 percentage point.
Percentage point.
And keep in mind, this is not going to be ranging from 0 to 100. This is ranging. This is not ranging from 0 to 1. This is ranging from 0 to 100. Because I called it a percent homeowners, or it'd be 8 or 16 or whatever. So in other words, we would say a 1 percentage point increase in the percent of people who own their homes results in 300,000, because it's entails increase in sales. For the week. Which admittedly seems pretty high, but you know, I don't know. People really love improving their houses. Oh, I think in the notes, I decided that it is actually, yeah. Sorry about that. In the notes, I decided it was ranged between 0 and 1. So we'll just make that note. So again, when I wrote the notes, so just to keep it consistent, I was thinking percent homeowners was actually between 0 and 1, not between 0 and 100. So you would take that 1%, convert it to 0.01. 0.01 times 300 gives you 3. And then because it's in thousands, it'll be 3,000.
Any questions? I don't know, it makes more sense anyway. That's all we need to say. All right. Any questions?
Okay, let's throw in a dummy variable. Again, this is all going to be hypothetical. GPA minus so this one uses a dummy variable as a dependent variable rather than an independent variable. And we're asking, is this individual employed? And we predict if they're employed or not based on their GPA. Maybe this is like they just graduated from college or something, so this was their GPA in college, hypothetically. And if they're female or not. What does that mean, by the way? If the observations equals 1, what does that mean? The observation, female or male? Female, how do you know? What? Because 1 means yes. That's why I personally, and I think I've seen this a few other places, but I personally like to structure my dummy variables as question marks, as questions. Because then 1 means yes, 0 means no. And then you immediately know what 1 is and what 0 is, yeah.
So for the employed dummy variable, because it's going to be like so hard for somebody to get like a 1.0 on the die, like is there kind of like a range?
What do you mean? For the female?
No, for
the employed? Yeah, well, let's see what that means. So I'll show you what it means in a moment. Let's see what it means. Let's imagine that we have these different numbers that I have in my notes, so you can do it multiple times. A GPA of 4.0, and the person is indeed a woman. And by the way, I made it slightly less likely because we know from the numbers that women are less likely to enter the workforce, that are more likely to do childcare. And that's what I be sexist. What do I think of myself as? But that's just why I made that negative. Why? Well, what would the value of employed be? You want it? 0.8. So what would that mean then? So a person with a GPA of 4.0 and a woman, and their employed variable is 0.8. What do you think that means? I like that, but not even most likely that they are employed.
80%.
There's an 80% chance they are employed. Because for any one observation, you checked that the person in observation was employed or not. You asked them. They said no. Oh, that's 0. There's a 0% chance you're employed because you're not employed. You said so. Check someone else. I am employed. Oh, there's a 100% chance you're employed because you said so. Right. 1. Here we have 0.8. So for this individual who's maybe about to graduate from school, what are the chances I'm employed? 80% chance. And that's how you can interpret a predicted dummy variable.
Is the GPA no higher than 4?
Nope. That's why I set it up this way.
Never 100% chance.
Nope. There's always market conditions. Maybe you have to adjust for major too. Maybe they majored in something, silly. This leads us to something else that we have to be careful about interpreting. a 1 point increase in GPA means what? A 1 point increase in GPA.
8% more likely.
No. Close.
Yeah, 8%.
8 percentage points more likely to be employed. Means the person, I should say the person, is it takes some getting used to, but that's points. Good boy.
Are you following? This sort of workshop. It's a smart part. It's really interesting. So,
This is a very important sentence.
this sentence is essentially an interpretation of the key variable, an interpretation of a variable in everyday language. When you write your memo, I ask you to take one particular variable and make it that key variable, the one you're most interested in, the sort of focus of the paper. And then the other two variables are controls. And you know, your focus will be the one that you pick. I don't care which one you pick, just make it interesting. And as you present your analysis, you then will need to add this, which is sometimes what we call the punchline. It's if someone could take away one idea from your paper, this is the one they should take away. This is the most important result. This is the interpretation of your key variable. I want to know how important is GPA to get employed anyway, Professor Yemmer. I ran the regression, and it turns out for every point in GPA means you are 8 percentage points more likely to be employed. It not only gives me the direction, obviously it's statistically significant because otherwise it wouldn't matter, so I'll say it's statistically significant, but it also tells you how much it matters. Any questions on that? Yeah.
So if none of ours were statistically significant, you don't have to go back and find a variable and listen to that.
Or you say it doesn't matter. So the option or the possibility that your variable, your key variable, is not statistically significant is interesting. In a lot of research, there's such a strong emphasis to make statistical significance because that's the interesting result and not is not interesting. And that's a problem. So I like to do my little part and move you away from that. Sometimes it not being statistically significant is also interesting. Everyone thinks that this matters. And so if you don't get statistical significance, you would say, look, people think that this matters, but it doesn't matter because of these reasons that, you know, maybe cancel out the reasons it does matter. And then you give the evidence, say, look, it doesn't matter. And your punchline is like, look, when you increase it, it doesn't matter. For all intents and purposes, this coefficient is 0. Right. You haven't proved it is because you don't really know, but that's when we fail to accept the null rather than just accepting it. But you fail to find evidence that this thing that everyone says matters. And that brings me to the memo the sample memo I did. Remember when I ran that regression? And I found that gender didn't matter at all for predicting the exam score. I could be like, everyone thinks gender matters. Didn't matter here. Maybe everyone else is a sexist, right? Or so whatever it is. Right? Maybe something fishy is going on, right? Because I didn't find any evidence that it mattered. Any questions? Jeanette, you have something? No? Quick, and you can answer my next question because I don't want you to be bored. You're not bored? Great. Then you should be really excited about answering this next question. So recall that, and I can't remember the exact numbers. So I don't remember what the beta value was on my sample memo or the total on the exam. I do remember that the time was 0.7, and then I had some controls which we're going to ignore. So how would you interpret this? Keep in mind that time is measured in minutes. An exam is just points.
Every additional minute, your
This is exam total.
so your exam total will increase by 7%.
So exam total isn't a percent. It's just, you know, based on.
Your exam total will increase by 7%.
Close. The farther away. 0.7 points, right?
Okay.
Because that's my. It's really the crucial thing is that is this a dummy variable? Is this a percent? If it's neither, then you're just going to interpret it normally 0.7 points, because this is measured in points. And that's kind of awkward the way I presented that, right? If we present it that way, for every additional minute, you get 0.7 points. Can you get 0.7 points on one of my exams? No. Plus, it's like sounds weird, like 0.7 points. It's in point twice. It's weird. So, do you know what I do in the memo? I don't even think people have seen the memo yet. Oh, you can't look at it yet? Okay. Well, I'll fix that. Oh, that's right. That's been messy. What I do in the memo is I
10 minutes and then 7.
I say for each additional 10 minutes. Spent on the exam. The exam score increases by how much? By 7 points. Right? And what's nice is that's a much more intuitive way to present that's exactly the same thing. Rather than saying an additional minute gives you 0.7 points, it's kind of awkward, right? You say, look, spend 10 more minutes, you'll get 7 more points. All right. Not only tells me it's statistically significant, because if it wasn't statistically significant, I couldn't say this. I would have to say it doesn't matter. 2, it tells me the direction, more time, more points. And 3, most crucially, it tells me the magnitude. It tells me how much you get. So when I did this first many years ago, and I ran that regression, I was like, cool, I got statistical significance. I'll be so interested. And I told my next I think it was the next semester, I told my classes, hey, 10 more minutes on the exam, and you'll get 7 more points. Right? Now, that's the relationship, right? So you should really spend more time on your exams. Well, I mean, I think I had people take more full time, but I ran the regression again, right? I was curious to see, I wanted to increase my sample size. So again, I recorded when people turned in their exams after I told them this, and I ran the regression again, and guess what I found? It wasn't statistically significant at all. Didn't matter at all. And what do you think happened? I think I know what happened, but I don't have data to support it, but I have a suspicion. What?
Yeah, it's more like it muddled up my causal story. So my story was to take more time to do the exam. I'm assuming you're using that time correctly. I'm assuming you're going back to check your work, make sure you don't miss anything that you skip over, again, cut out any stupid errors or rethink things. That's what I'm assuming. That was my justification for it. And that's what I say in my proposal, right? This is why this connection. But what I think happened is that students here, for every additional 10 minutes, I get 7 more points. Great. Professor Younger said if I just wait, I'll do better. I'm going to wait 30 minutes. And this is like, I'm just going to stare blankly. I'm going to do it. And I'm assuming you're using the time for that, so that, of course, no. That's why I think it didn't get statistical significance anymore. But you want to actually check to see if they took one. That would be evidence. Any questions? Okay. We're a little. Let's Let me do this one really quickly. So now a hypothetical one on percent of people who are happy.
They are happy with their pizza delivery.
And so this is also going to be ranged from 0 to 1. And I'm going to predict happiness with their pizza delivery based on the price of the pizza. Based on, there really should be a plus. No, it should be a minus. Based on time, how long it took to deliver the pizza, and then based on how much cheese it had, measured in pounds. I don't really know how they measure how much cheese they put on a pizza, but I decided to measure it in pounds. Now, does anyone see anything odd about this?
The 1.3 is like so big compared to all the
Yeah, the 1.3, it's like, not only is it big, but if this is ranged from 0 to 1, I start with something way above 1. That's weird. But it's okay. Why is it okay?
Because you're more likely to happen to be doing things that you want. So you have a higher chance of being happy since you ordered the pizza.
Sure. But think in terms of how this, even though it's hypothetical, this would have, if I had it, came from an actual data set. So
you're always going to have like a set price. There's always going to be some sort of price that's going to take away from that 1.3. There's always going to be like a set like minimum time that's always going to take away. So it's always going to take away like some sort of 1.3. That's going to be that max of the cheese.
yeah.
So like it can only like you're expecting the price of the time like, to come down automatically to bring the 1.3 down automatically.
Exactly right. It has to be. Right? Because there's no, I'm not going to include any like pizza that was free or any pizza that took 0 amount of time to be delivered. Right? Exactly the case. Like if this pizza took 10 minutes to be delivered, immediately I'm going to be subtracting off 0.5. And 10 minutes for a pizza is pretty fast. If I have a $5 pizza, which is a really cheap pizza, I'm taking off 30.25. Quite frankly, I probably should have started at a higher cutoff point. Of course, then they put cheese on it. I don't know how much cheese on the pizza. But anyway, don't be confused by that. And again, we would interpret this as percentage point increase or percentage point decrease. For every additional dollar, 7%, there's a 7 percentage point decrease in the percent of people who are happy with their pizza.
Any questions? Let's go over to what's on the next one. Let's use the memo data size. Let's use the memo one. It's fun to work with, especially as we move forward. So, for maximum work on it, people don't want the countries. Let's work with the country data. Maybe actually faster for the
for everything.
yeah, let's work with the state data. Let's work with the state data this time. So, if you go all the way to the right on the children waiting to be adopted section, some wild fluctuation in this. You'll
note that California has over 12,000 children waiting to be adopted, and Alaska only has 700 children. Is it the case that California is filled with jerks who don't want their kids? And they're just terrible people in California? All sunshine, they're like, I'm going to have kids, I want to be able to be in great shape and just party all night. And Alaskans are like really just like wonderful people who really, Delaware is 294. Is that what's going on? Rebecca?
No, the population is small.
Oh, population, we got to throw off the population, right? So we have to adjust the population. Now, I already did that here, but I want to show you how I got here. So, for one, let's just delete the District of Columbia, because you can see we don't have data for District of Columbia. So we're just gonna ignore it. And I don't want to deal with that empty cell later, so we'll just delete it. And I'm gonna right click PM and insert. And this is going to be let's say adopt. Way to adopt per capita. So we know what per capita means. Per person, right? And as a side note too, when you see GDP per capita under the country data, if you look at the country statistics, you see GDP per cap is also known as average income. So keep that in mind if you're looking for average income data and the country level data, that's the same thing as the GDP per capita. Capita being Latin for what? Person. Well, Latin for head, but person. Okay. So how would I? So I want to move this away. How would I do this? How would I find way to adopt per capita? What would my first thing I should do? How do I figure that out? Anyone? Austin? Austin, you here? Charlie. Charlie, well, why would you do this?
Take like the population divided by the total children.
So you want to start right. We want to find a new variable
That is children waiting to be adopted per capita. If we take the child divided by the population, is what we want. We would get some new variable x. Right. Agreed? Some new number x. Right. We recognize that that is the same thing as x divided by 1. Do we see that? So in other words, and that 1 would be expressed in whatever you put in the denominator. So this is child per person. Child per person. So whatever you want to be as the per part is what you put in the denominator, not the numerator. So we wouldn't have population divided by kids, we would have kids divided by population. Which I believe I have all the way. I'm going to put that. What was it? Y. Oh, there it is. Yeah. I threw it over there. So BN3 divided by Y3. And then you copy and paste it now. Yeah, so you're just doing normal ones. Yeah. This is not helpful at all. Why is it all a bunch of zeros? Yeah. Right. Now, granted, we could, if we want, add some decimal places, but now it's just terrible. It's like, what am I supposed to do with that? Oh, wow, I really like. Let's see. Okay, fine. Alabama has, for every person, 0.00027 kids waiting to be adopted. making any sense. How am I supposed to use that? So in this case, we have to add a scalar. A scalar is a constant value multiplied by observations to make regression interpretation easier. You can use a simplified regression interpretation.
So that's the same thing when you were talking about like 7 minutes or whatever.
Well, that's a little different. I was just I mean, it's a similar idea, but I was just multiplying it more like I was changing the change from a change of 1 minute to a change of 10 minutes, and then I was just multiplying by the coefficient. This is me actually changing the variables. Someone last class asked about, like, I might use, one variable that's per 1,000 people and another variable that's per 100,000 people. Is that a problem? That's fine. That's not a big deal at all. Because they're both being adjusted to population. They just have a slightly different scalar. But it doesn't really matter. As long as you're adjusting the population. The population is going to be different for every observation, for every state. But the scalar is going to be identical for every state. So it doesn't matter if you have a scalar for one and not a scalar for others. It just makes things a little easier, makes things easier to interpret, and makes things more intuitive. So let's add a new column. Let's reproduce, again, I saw that in line. Let's reproduce the, what I have over here, 400,000. Reproduce it over here. So I'm going to remove that line to, there we go. We're looking at increasingly stupid. And this is weight to adopt per 100K. That's this one, per 100K. How would I do that?
That's the numbers we got.
So we can, remember, we can multiply anything by 1. So we can take, divide anything by 1 into the same number. We can multiply anything by 1 into the same number. And I'm going to multiply this by 100K divided by 100K. Which means if I'm going to multiply each one of these by 100,000, this becomes a new variable. We'll call it x sub 100. So 100K divided by 1 times 100K. Now we have a number per 100,000 people. Just like we had over here, a number per 1 person. So in order to get that, I'm just going to take this and multiply it by 100,000. Oh, that's going to actually go with 97 per 100,000. But you can see, what I should count. And these are consonants. They're exactly the same. That's exactly how I calculated these values. 26.88, 26.88, 97.75, 97.75, etc. That's what that comes from. You don't see that because I then copied and then pasted the values to get rid of the actual equation. That's exactly the same. Any questions? Yeah. What? Oh, sure. That's the
let me actually change one of the things before I do that. Let me go into view and unfreeze panel. There we go. Now you can actually see something. There we go. Yep, no problem.
I thought we should have put an extra photo, whatever.
Any other questions? My next question for you
Is how do you think using a scalar changed the regression? So,
to illustrate what's going on, you need to make sure that you have what's it called, the analysis active. Let's show you what's going on. Data analysis, regression. Let's see. I would like to have waiting to adopt. I would like that to predict. A little more. It doesn't matter what I choose. No one ever picks these poor little caches. Let's pick the cache in this one. No one ever picks that for regression analysis. So we'll use that. You did? Very few people pick that. I think you picked it. Good man. Okay.
So what I did is for why I'm predicting cash flow analysis, I'm trying to predict that using children out per capita. I just done children waiting to be adopted per capita. There's no story at all here. I just want to show you a regression analysis. In fact, I want to show you two regression analyses.
This one. And then another one right next to it. But this one uses it as where you adopt from reference. And then the alpha range will just be right next to it.
See the big question we're seeing.
Here, I'm going to make that space. I don't know if you can see that. I'm going to delete some stuff that I know we don't need. Delete that. Oh, interesting. I'm actually going to move the second variable, the second regression down here, so you can just compare them a little bit. Yeah, that's better. Okay. So here I have the second regression.
I'm surprised by that. Here I have the second regression. Here's the first one, with them waiting to adopt per capita. Second one, waiting to adopt per 100,000. And both of them predicting cash flow. Now, what do you notice about statistical significance? Yeah, right. I was astonished by that. I didn't think it was that random. I didn't expect to get anything. Maybe there's a story there to think about. So here we have p-value, statistically significant. Right? How do we know it's statistically significant? Exactly. It's small. It's less than our minimum 0.05 threshold. It's less than maximum, I should say, 0.05 threshold. Less than certainly 0.01, less than even 0.001. Yeah, it's statistically significant. Not what I expected. What's the p-value for the second one? Exactly. Same exact thing. Not similar to, not kind of close to, exactly the same. Using a scalar doesn't change statistical significance. It does not change statistical significance. The only thing it messes around with is the coefficient. What's the difference between these coefficients?
Anyone?
They're just 100,000, 100,000 more times more.
Where the hell did my eraser go? I usually put it over here, and that's why I usually lose it. Oh, there it is. Yeah, it was just right there. So, to show you what's going on, let's look at my actual regression. There's my cache variable. I have some beta of 1, some beta 0, plus some beta 1, and then I'll just use the child for the variable. That's my basic regression, right? What did I do to the child variable? I want to sweep this over to 1 through. Plus beta 1. Exactly. I multiplied it by 100,000. Which means I can do that, just like I was doing before, right? I can multiply it by 100,000. And then divide by 100,000 is the same thing. As noted, this 100,000 became the variable that I was analyzing, which means this 100,000 was applied here. Times 100. In other words, it went from 7,452 to exactly divide that by 100,000, and you will get 0.07452. So you can, if you want a more intuitive looking coefficient, just change by a scalar. Keep in mind too, right, you don't want to have too many decimal places. So you could argue this is kind of small, but if I made it for like 10 million, this would be even smaller. That's way too small. Right? That's an awkward thing to interpret. But note also it makes sense that this happened, because when I was using it per person, this number was really small. So to bring this up to the cache value number, which is something like the 0 and 1 range, it had to multiply it by a pretty big number, this one. But then when I made it much more reasonable, in the 30s and 40s range, well, now to get up to that cache value number, it had to actually multiply by a smaller number to bring it down. Cancel it out. So scalars don't change significance, they only change coefficient. And they change coefficient by the reciprocal of however you changed the original data. I multiplied the data by 100,000, thus I divided the coefficient by 100,000. And it cancels out. Any questions? As a side note too, in a little bit of time I have left, had I swapped these around and made catch predict child out all, and I then multiplied the child by child rate of reduction, and then multiplied this by 100,000, then this is the stuff that would be multiplied by 100,000. Right, then the beta value would be 100,000 times larger, and the beta 1 would be 100,000 times larger as well. Just by the simple algebra. If, by the way, I do go over this because there's one variable in the memo data set. If you look at the countries, it is not just a population, but realistically. And that is the child out of all school. And it is also the child managing that. This one. Child out all, the number of kids that are out of school. That really should be adjusted for population. You can adjust it by population by just doing what we did here and taking the number divided by population. Or if you want to be really fancy, there's also data on the percent. There's like a percent of the population that's 0 to 4, and the percent of population that's 5 to 7. You know those. If you figure out the percent of the population that is kids, then you get the number of kids, and then it can be a child out per kid, which is much better than population, because some countries are older populations, like Japan. Some countries are younger populations. So if you want to use that variable, that's a great way to do it. All right, with that in mind, I will let you go. Have a great couple of days, everyone. I will see you on Thursday.